You are the holder of a Burger King franchise and have determined that the demand for your single product is Q equals 6 minus 2P, where Q is in thousands and P is in dollars. You face two costs: royalties to BK, equivalent to 20% of your revenues, and cost of $1 per sandwich for ingredients and labor. The two questions I want for you to focus on here. The first question is, how much profit do you make when you maximize sales revenues? And the second question says, determine whether you can do better for yourself than maximizing sales revenues. You might want to stop and read the case from chapter 2. So you would probably want to hit pause on the video, or alternatively, you might want to go to your textbook and read it at your leisure. I've prepared a summary of the key statements, the key facts in this particular case, for which you have to do the analysis. Here is my summary. The franchisor increases sales revenue by increasing the number of franchises. The franchisor collects a fixed percentage of sales revenue from franchisees, for example, 20%. Franchisor increases sales revenue by increasing advertising and determining other strategies to optimize sales. And the franchisee's objective is to maximize profit. This conflicts with the franchisor's objective, which is to maximize sales revenue, because the franchisor takes a percentage of your revenues. So here's our problem again, a made-up problem. I give you the demand, or the inverse demand. The demand for the BK burger is Q equals 6 minus 2P. It's in thousands. I can rewrite that equation as P equals 3 minus and in order to get to the revenue, I multiply the price by quantity. So from this equation, I multiply each side by Q, because revenue is price times quantity. So I multiply on the left-hand side and I get R revenue, which is P times Q. I multiply by Q on the right-hand side and I get 3Q minus 0.5 Q squared. I point out that the costs are twofold. First, the cost of production, $1 per sandwich, and then the royalty costs, which is 20% of the revenues that the franchisee makes. This helps us to construct the cost function. C equals 20% of the revenue plus $1 per sandwich, and therefore the coefficient on the Q term is understood to be 1, the $1 per sandwich. We determine profits by multiplying price times quantity to get revenue and subtracting the cost from the revenue. So if I were to take the two equations for cost and revenue, so I subtract 20% of the revenue from 100% of the revenue, and that's where I get 0.8, which is 1, or 100%, minus 0.2, or 20%. 8 of the revenue is what the franchisee gets to keep, and then he subtracts the cost of production. 3 times 0.8 is 2.4. 2.4 minus 1 gives me 1.4 as the coefficient on the Q term. 0.8 of 0.5, half of 0.8 is 0.4. So that explains the coefficient on the Q squared term. The profit function is now determined, and we do the best we can. The first objective is to maximize sales revenue and determine the profit. To maximize sales revenue, then, we need to go back to the revenue function. From the revenue function, we would differentiate the revenue function. So the differential of 3Q is Q, and the differential of 0.5 Q squared is 2 times 0.5 equals 1, 1Q. And that's a minus, so we get the differential to be 3 minus Q. Set it equal to 0. That means that you're asking the question, where on the revenue function is the slope going to be equal to 0? Remember, the differential dr dq is really asking, what is the slope of the revenue function? 0 here asks, where is the slope of the revenue function equal to 0? If you sketch the revenue function, it would be an inverse U shape. As you look at the revenue equation, you can see that as Q increases, the revenue will increase. But there's a minus on the Q squared term, and that's going to pull the revenue curve down, so it's going to rise or increase at a decreasing rate. It has a maximum, and then it falls after that point. The slope of the revenue equation is equal to 0 when Q is equal to 3. Remember, this is in 1,000. Q equals 3,000. You plug Q equals 3 back into the demand equation. Half of 3 is 1.5. 3 minus 1.5 is 1.5. And that explains why the price is 1.5. The revenue is price times quantity, so 1.5 times 3 is 4.5, again in thousands. The cost is 20% of the revenue, so 20% of 4.5, plus the cost of production, which is $1 per sandwich, that's going to be 3 or 3,000. 20% of 4.5 is 0.9, plus 3 is 3.9. The revenue is 4.5, so 4.5 minus 3.9 gives us 0.6. Our profit is going to be 0.6 thousand, or $600 per week. The second question asks whether you can do better for yourself than maximizing sales revenue. To maximize profit, we differentiate the profit function. We call the profit function pi equals 1.4q minus 0.4q squared. And we get the differential of 1.4q is 1.4. The differential of 0.4q squared is 0.8q. Since the differential is the slope of the profit function, we ask the question, where is the profit function maximized, i.e. where is the slope of the profit function equal to 0? We solve the equation 1.4 equals 0.8q, and that gives us a quantity of 1.75 in thousands and a price of 2.125. Multiply price times quantity, or revenue is going to be $3,718.75. Our costs are going to be $2,493.75, so that the profit is going to be $1,225. $1,225 is more than twice as much as $600 we earned when we maximized sales revenue and took whatever profit came as a consequence of that calculation. So clearly maximizing profit does better for the firm. The table you see contains only whole numbered quantities. Again, these are in thousands. So we're looking at Q equals 1,000, 2, 3, 4. The price is a consequence of the inverse demand. P equals 3 minus 0.5Q. So when we plug in the values for Q, we can get P. Revenue is price times quantity. This is in column 3. The numbers highlighted in red are the values for the revenue maximizing problem. You notice the cost of 3.9. 4.5 minus 3.9 gives us 0.6 in thousands. It is easy to see in the analysis that we're looking at that the price of 2 and the quantity of 2 give a revenue of 4. It gives a variable cost of 2, and 20% of 4 is 0.8. This gives us a cost of 2.8. 2.8 from 4 leaves us with a profit of 1.2. And clearly, by charging a higher price, higher than 1.5, we're going to see the profits increase. Notice that because we're only dealing with whole numbers here, we don't get to see the 1.75, which is the quantity that maximizes profit, or the 2.125, which is the price that maximizes profit. But the table gives you an idea of how you can increase your profit by cutting back on the quantity you sell and charging a higher price. I hope you can understand how this would be a conflict, because the franchisor would prefer for you to maximize sales revenue, and 4.5 is clearly a higher sales revenue than 4. But the franchisee would prefer to maximize profit, and therefore charging a higher price and selling a smaller quantity is more likely to do that. The inverse demand curve you see sketched here has the vertical intercept of 3. The slope is the rise on the run, 3 over 6. That is 1/2, the negative slope, 3 minus 1/2 Q. A is the midpoint of that linear demand curve, so the price is going to be halfway up the vertical axis. The vertical axis is maximum at 3, so 1.5 is the midpoint. On the quantity axis, 3 is the midpoint, halfway point between 0 and 6. Point A then is the revenue maximizing price quantity combination. Please note that we're walking up the demand curve to the northwest of point A, and the point B represents a smaller revenue but a higher profit. This is based on the data in the table. Our calculation showed that even higher price, 2.125, would yield an even smaller quantity, 1.75 in thousands, and the profit would be even larger than 1.2. My conclusion is that based on the options in the table above, the franchisor would prefer the franchisee to operate at point A, whereas the franchisee would prefer to operate at point B, but yet our calculation shows that we will go even further, and a point such as point C, right about here, even further to the northwest of point B, would maximize the profit for the franchisee.